Hello and welcome to my talk that revisits description logics with concrete domains and general concept inclusions. My name is Jakub Redval and this is joint work with Franz Bader. This work was supported by the German Science Foundation DFG within a doctoral program on quantitative logics and automata. Description logics are logic-based formalisms used in knowledge representation. Most of them are decidable fragments of first-order logic. In this talk, we focus on the description logic ALC, which is contained in the two-variable fragment and also the guarded fragment of first-order logic. It describes objects and relations between them using the so-called ALC concepts, which are built inductively from atomic formulas as follows. Unary formulas that take the form of a single positive literal, the full unary predicate or the empty unary predicate are concepts. Also, Boolean combinations of concepts are, again, concepts. And finally, if we have a unary formula phi that is a concept and a binary relation symbol R, short a role, then the existential restriction and the universal restriction via R are concepts. One uses the following compact notation for concepts instead of writing down complete first-order formulas. The interpretation of a concept C in a model I of ALC is denoted by C with an upper index I. Concrete domains allow concept descriptions with predefined structure, such as age, location, or size, which cannot be expressed in ALC alone. The following is an example of a concept which describes individuals who are humans and who have a parent and a grandparent of identical age. In realistic models, this concept should be interpreted as the empty set. On the next slide, we will see a simple condition formulated in ALC equipped with the set of ordered rationals as a concrete domain, which ensures that this is the case. But first, let us take a look at the formal definition of how a concrete domain is included in ALC. Let I be a model of ALC and D a relational structure with a signature tau. We introduce new symbols for partial functions from the domain of I to the domain of D. If phi is a k-array first-order tau formula with three variables x1 to xk, r1 to rk are binary relation symbols, and f1 to fk are partial function symbols, then the existential restriction via the paths rj, fj, and the formula phi is a concept. This concept is interpreted in a model I of ALC equipped with D as a concrete domain as the set of all individuals x with rj neighbors for each j, such that the fj values at these neighbors form a tuple that satisfies the formula phi in D. We also allow empty roles, which refer to the individual itself, as in the example above. The universal restriction is defined analogously. It is interpreted in a model I of ALC equipped with D as a concrete domain as the set of all individuals x, such that whenever there are rj neighbors for each j, whose fj values are defined, then the fj values form a tuple that satisfies the formula phi in D. A GCI is an expression of the form C1 subsumed by C2 for concepts C1 and C2 that is satisfied in a model I of ALC if the interpretation of C1 in I forms a subset of the interpretation of C2 in I. GCIs generally serve as knowledge bases for reasoning with ALC. The main decision problem for ALC is concept satisfiability with respect to GCIs. As an input, we get a concept C and a GCI. The problem is to decide whether there exists a model of ALC which satisfies the given GCI and where C is interpreted as a non-empty set. As an example, let us consider the concept from the previous slide describing a human who has a parent and a grandparent who are of the same age, and the GCI telling us that every parent of a human being is a strictly older human being. To see that this instance is unsatisfiable, we proceed in two steps. First, we use the initial part of the GCI to infer that all present individuals are humans. Then, we use the second part of the GCI to obtain an unsatisfiable system of ordering constraints over the rationals. Concept satisfiability with respect to GCIs is X-time complete for ALC itself. The problem stays decidable for ALC equipped with ordered rationals as a concrete domain, but the resulting DL loses the finite model property. For ALC equipped with a successor relation on the natural numbers and the constant zero, the problem becomes undecidable. This result is due to Lutz. Our first contribution is showing that it is undecidable even if we drop the constant zero. We could also replace natural numbers with integers, rationals, or reals. Similarly, as in the proof of the original result, we proceed by a reduction from the halting problem for two-register machines. We translate states into concepts, registers into partial functions from models of ALC to the concrete domain, the transition function into a role G, and the in- and decrementation instructions into GCIs. However, our proof does not rely on having the constant zero for zero tests. Instead, we introduce a partial function 0 that stores an arbitrary natural number, and its value is propagated to all G successors for future comparisons. In 2007, Lutz and Milicic isolated a sufficient condition for decidability of concept satisfiability with respect to GCIs in ALC with concrete domains. They call this condition omega admissibility. In their setting, the formulas present in the concrete domain constructors were restricted to disjunctions of positive binary literals. A structure D is omega admissible if it satisfies the following 5 conditions. First, D has a finite binary relational signature tau. Second, its relations are jointly exhaustive, short JE, and pairwise disjoint, short PD. Third, the constraint satisfaction problem of D, short the CSP of D, is decidable. This is the problem of deciding for a given finite tau structure A, whether A homomorphically maps to D. Before we proceed to the fourth and the fifth condition, let's look at 2 examples of structures which satisfy the first 3 conditions. The first example is the set of ordered rationals expanded by the equality predicate and the inverse order relation. The CSP of ordered rationals is known as the digraph acyclicity problem and is solvable in polynomial time. The second example is the set of 3 colors equipped with the equality and the inequality predicate. Without the equality predicate, this structure is simply the complete graph with 3 vertices. Its CSP is known as the 3-colorability problem and is solvable in non-deterministic polynomial time. The fourth condition of omega admissibility is called the patchwork property. It requires that for all finite structures A, B1, and B2 with jointly exhaustive and pairwise disjoint relations, such that A embeds to B1 and to B2, while B1 and B2 both homomorphically map to D, there exists a second pair of homomorphisms from B1 and B2 to D that commutes with the original embeddings from A. By an embedding, we mean an injective homomorphism which preserves complements of relations. Finally, the fifth condition, called compactness, requires that the countable tau structure B maps homomorphically to D if this is true for all of its finite substructures. Lutz and Milicic presented the following examples of omega admissible concrete domains. Allen's interval algebra, which describes all 13 possible relations between time intervals, and the region connection calculus, which describes all 8 possible relations between regions of a Euclidean space. In general, it is difficult to verify the patchwork property and compactness for a given concrete domain. However, we claim that these conditions are actually known from model theory. We now introduce three model theoretic properties of relational structures and show their connection to omega admissibility. We start with omega categoricity, which is sufficient for the compactness property. A structure D is called omega categorical if its first-order theory has a unique countable model up to isomorphism. A good example is the set of ordered rationals. The first proof of omega categoricity of this structure is attributed to Cantor. He used the back-and-forth method to show that there exists an up to isomorphism unique countable dense and unbounded linear order. The famous theorem of Engel, Relnarchevsky, and Svenonius provides two alternative definitions of omega categoricity. A countable structure D with a countable signature is omega categorical if and only if, for every k, only finitely many k-ary relations over the domain of D are first-order definable in D. If and only if, every relation over the domain of D that is preserved by all automorphisms of D is first-order definable in D. An automorphism is a bijective homomorphism from a structure to itself, which preserves complements of relations. The fact that omega categoricity implies the compactness property is a known consequence of this theorem. We now start building up a construction that will ultimately lead to the proof of our main result. For a given omega categorical structure D with at most d-ary relations, where D is some natural number, we replace the relations of D by the orbits of all at most d-ary tuples under the automorphisms of D. An orbit of a tuple is the set formed by an application of all automorphisms of D to the tuple. For instance, the orbit of the 4 tuple with the entries 2, 3, 2, and 5 under the automorphisms of the ordered rationals is the set of all 4 tuples of rational numbers whose first and the third entry are equal and less than the second entry, which is less than the fourth entry. We refer to the structure resulting from the replacement above as the D-reduct of D. Note that the relations of D are unions of the relations of the D-reduct. This is because they are preserved by all automorphisms of D and thus contain with each tuple also its orbit. By theorem of Relnarchevsky, the relations of the D-reduct are first-order definable in D, as they are preserved by all automorphisms of D, and they are also clearly jointly exhaustive and pairwise disjoint. Furthermore, the equality predicate is the union of some relations of the D-reduct. We say that the D-reduct is jointly diagonal. And, most importantly, the D-reduct has only finitely many relations. This would not necessarily be the case if we started with a structure that is not omega categorical, such as the integers with successor, which have infinitely many orbits of pairs. To obtain structures with the patchwork property, we restrict our attention to those which are homogeneous. A structure D is homogeneous if every isomorphism between its finite substructures extends to an automorphism of D. Our running example, the set of ordered rationals, is homogeneous. If we have two isomorphic finite substructures of ordered rationals, that is, two finite linear orders of the same cardinality, then we can extend this isomorphism to a piecewise linear transformation, which is an automorphism of ordered rationals. In the case when the signature of D is finite, homogeneity implies omega categoricity. Frase's theorem characterizes countable homogeneous structures as those whose finite substructures form a class that satisfies the amalgamation property, which is suspiciously similar to the patchwork property. A class K of tau structures has the amalgamation property if for all A, B1 and B2 from K, such that A embeds to B1 and to B2, there exists a structure C in K, together with a pair of embeddings from B1 and B2 to C, which commute with the original embeddings from A. we can link the amalgamation property to the patchwork property, under the assumption that D is jointly diagonal, jointly exhaustive, and pairwise disjoint. We have shown that if D satisfies these three properties, then the patchwork property for D is equivalent to the amalgamation property for the class of all finite substructures of D. Let us summarize the results so far. If D is homogeneous in a finite signature, then it is omega categorical, and thus its D reduct has a finite signature as well. Furthermore, the D reduct is jointly diagonal, jointly exhaustive, and pairwise disjoint by its construction. And it has the patchwork and the compactness property. Finally, to ensure that the CSP is decidable, we restrict our attention to finitely bounded structures. A tau structure D is finitely bounded if tau is finite, and there exists a finite set N of tau structures such that a finite tau structure B embeds to D if and only if no structure from N embeds to B. Alternatively, a structure D with a finite signature is finitely bounded if there exists a universal first-order sentence such that precisely the models of the sentence can be embedded to D. Our running example, the ordered set of rationals, is finitely bounded. It has a simple set of four bounds consisting of the loop, the directed 2 cycle, the directed 3 cycle, and the disjoint union of two isolated vertices. These four bounds enforce the known axioms for finite linear orders: irreflexivity, asymmetry, transitivity, and totality. It is known that if a structure D has finitely many relations, all of which are first-order definable in a fixed, finitely bounded homogeneous structure, then the CSP of D is decidable in NP, and its first-order theory is decidable in P-space. Using this upper bound for the CSP, we get that the D reduct of a finitely bounded homogeneous structure is omega admissible. A reduct of a structure D is formed simply by dropping some of its relations. Our main result states that concept satisfiability with respect to GCIs in ALC with a concrete domain D and arbitrary D-ary concrete domain formulas is decidable if D has at most D-ary relations and is a reduct of a finitely bounded homogeneous structure. The proof essentially boils down to replacing every such formula with a disjunction of formulas defining orbits, which can be performed in P-space, and then replacing D with its D reduct, which has the orbits as its relations. For the D reduct, we can use a version of theorem of Lutz and Milicic generalized to higher arities to obtain decidability. The class of reducts of finitely bounded homogeneous structures is quite rich. It contains, for instance, the homogeneous representations of Allen's interval algebra and region connection calculus, as well as the ordered rationals. It is closed under expansions of structures by finitely many constants, under disjoint unions, and certain products. In conclusion, we have shown that a known undecidability result for ALC with concrete domains can be further improved, that omega admissibility is closely related to known notions from model theory, and that finitely bounded homogeneous structures yield omega admissible concrete domains. We expect that these results will be useful for locating new omega admissible concrete domains. In particular, because finitely bounded homogeneous structures are currently the main object of study in the infinite domain constraint satisfaction community. For instance, Bodilsky, Knoyer, and Starke have recently proved that for binary signatures, it is decidable whether a finite set of bounds describes a finitely bounded homogeneous structure. This means that, given a finite set of bounds with binary relations, one can decide whether there exists a concrete domain specified precisely by these bounds that satisfies our sufficient condition for decidable reasoning in ALC with concrete domains. This completes my talk. I'm happy to take questions.